RS-FlipFlops are digital components that can store their state until they are being set or reset. In this video we will see how they are constructed and how they work. Part 1. The RS-FlipFlop has a reset input, a set input, an output called Q, and an inverted output called not Q. It consists of two NOR gates. And this is a circuit in which we can analyze the flip-flop. The circuit contains a power supply that's boring but needed. It also has two sources as input signals, which are also boring. And it has the flip-flop, that's the interesting part here. Alright, let's simulate it. At the beginning of our simulation, the purple reset input is high, the flip-flop is in reset state. We can see this state because the green Q output is low. This state is stable, nothing changes, until we give it a signal to set. Now this NOR gate says, alright, my NOR condition is no longer fulfilled, I'll have to make a low output. It switches off the red node. Then the upper NOR realizes now neither my purple nor my red input is high and I'm a NOR gate, so I have to make a high output now. So it does and turns on the green node. Now we have set the flip-flop. The high output status is now stored by the flip-flop, even when we turn off the set signal, until we give it the reset signal. In that case, the upper NOR gate has to switch off and the lower NOR gate has to switch on. The reset process is complete, and again we're in the reset state where we have been at the beginning. Part 2. There is a set reset flip-flop that is very similar to our first one. The set reset flip-flop has an inverted set input, an inverted reset input, and the usual two outputs. This one consists of two NAND gates. The first one was made out of two NOR gates, that's the difference. So again, we have a circuit to simulate the behavior of that flip-flop. With a power supply, boring. Two sources as input signals, also boring. And the flip-flop, that's the interesting part. Again, we start our simulation in the reset state. The reset state looks a little bit different than in the part 1 because inputs are inverted. But the principle is very similar. The reset state is stable and it is independent of the reset input. But of course we can set it. Therefore we have to turn the not set input to low. Then the upper NAND gate realizes, hey, my purple input is no longer high, I now have to switch on. So it does. And the lower NAND has to turn off. So it does. The set process is completed. Now we have a high output. This state keeps itself as it is, even when we turn the not set signal to true again. This state is kept until we give the flip-flop a reset command. And then the lower NAND has to switch on. The upper gate has to switch off. And the reset process is now complete. We have reached the reset state as we had in the beginning. Part 3, let's summarize. We have seen two kinds of different flip-flops. We have seen how they are constructed, and in the simulation we have seen how they work. If you want, you can create circuits like this with KiCad eSchema, and you can simulate and visualize them with the circuit navigation system. You can download both programs for free, and the links are given in the description.